Hi, I want to try and make a zero knowledge proof card game. I chose the game Tarok, and to get started I need to familiarize myself with the rules. So here I've got a notebook. So Tarok is a card game with 78 cards, and if you adapt it for just 2 players, it's similar to trumps basically. A player has to match the suit that the other player has played, and if they can't, they have to play a trump card. So what do we need to do in the code? We're going to need to deal the cards, and that's going to have to be done with some Web2. So they're going to get the dealt cards from the server. Then the user interface is going to use zero knowledge to prove that the hash that they're going to send to the chain includes the signed game ID. That gets sent to the chain. The chain verifies the zero knowledge proof and creates a game structure and then gives acknowledgement to the user interface. For someone to join a game, a similar process will take place. So in the user interface, a player will choose a game. They would send that game ID to the server with a Web2 transaction, and then the server would look up its stored data to see if that game exists. If the game exists, it will send back the hand of cards and that signature. Then the user interface would use a zero knowledge proof to show that the hash includes the signature of the game ID. The chain can then tie the player's hand to the crypto wallet, but the player hasn't revealed what is actually in their hand. And then to play the game, each person reveals a card using zero knowledge proof. So they pick a card they want to play, and they use zero knowledge proof to prove that that card makes up this hash, which is stored on chain. And then once that's done, the second player has knowledge of the card that has been dealt, because that's now visible on chain. And so the second player picks a card to play. I've sketched up some logic for playing the game. So 8 of swords. So as player 1 has played a card of the suit swords, player 2 needs to play a card of the suit swords. So he's going to play 6 of swords, and player 1 wins. So now player 1 has some less cards. 1 of pentangles. Now, as player 1 has played a pentangles card, player 2 needs to play a pentangles card. As player 2 doesn't have a pentangles card, there's nothing here that starts with a P, he is forced to use a trump card. So the next thing is to write a circumcircuit for a zero knowledge proof that a hash is made up of some attributes that you want to make public. Okay, so now we need to make a circumcircuit for the zero knowledge proof. Now, here I've created a React app. Inside here, I'm just going to make a new folder called contracts, and in here I'm going to create a hard hat project. And then in this project, I'm also going to make a circuits directory. We are going to need a hashing function. So there is a project by this group, ident3. We've got a circumlib project, and in here they've got a bunch of circuits which thankfully are already created. Now I'm going to use this hashing function, which is apparently a new hashing function created for implementation in Circom. So we are going to want to install this package. Also, we are going to need snark.js. So initialize your hard hat project as well. Create a JavaScript project. Let's write a circuit. We need to define the compiler. We're going to want an import as well. Import. You need to work out how to navigate to the library. Node modules. Circumlib circuit. In order to implement some logic in the circuit, we're going to need this circuit as well, the comparators one. Because in the circuit, we are going to be checking if the card that we pass as one of the input signals is in our hand of cards. So I will be using is equals and is 0. So the signals we are going to need are the card, and then we are going to want an array of cards. The cards will be represented as just numbers, 1 to 78, and each hand has 8 cards. And then we are going to have the RSV values of a signature of the game ID. One of the constraints of compiling a zero knowledge proof using Circum and SnarkJS is that the signals have to be less than this number. That's in the documentation somewhere, and it has something to do with the cryptography involved. So what I'm just going to do is I'm just going to bit shift the R value, stripping away 8 bytes, and bit shift the S value, stripping away 8 bytes, and then I'm going to add those 16 bytes to the V value, which is just 1 byte. If you don't do that, the compiler will make you aware of that. Okay, so we have these values. Then what we need to do is hash them. Sponge. And the initializer is we need the number of inputs. The number of inputs is 11, and here we've got the number of rounds. It explicitly states the rounds should be 220, and we just want one output. Then we need to pass these input signals to this hashing component. Okay, so C hash ins, we're going to be populating this input signal with the number of inputs. Okay, so we've got our 8 cards. Next we'll put in the signature values, our main, and then the output signal is just the output of the C hash component. So we've just basically wrapped this generic hashing component. And now we need a main declaration. So we state the public signals. So that's great for starting a game, but for playing the game we also need some logic to prove that this card, which is given as an input, is included in the array of cards. To achieve that, if the card's 0, I'm going to bypass asserting if card is in cards. Initialize some components. Then we have a for loop, and in the for loop we initialize each of the array of components is equal, and we're going to pass the card as the first, and then we are going to pass the item from the array of cards, and then we are going to take the output signal, which is called equal, and add it to our tally variable. If this card is in this array of cards, the variable tally will be equal to 1 after this for loop. Okay, so you can assert a Boolean value. we're going to do assert tally equals 1, meaning that card is 0.out is 1. So we've got the compiler version, we've got our imports, we've got our template, we've got the input of the card, and we've got the input of the cards. We've got the input of the signature. We initialize the components we're using for the logic. We loop through each of the cards to check if it is equal to the card we want to show. We assert that either the card we pass is equal to 0 or the tally is equal to 1, which means we are showing a card that is in our array of cards. Then we do the hash function, we return the hash. And these are our stated public signals, so only this signal is hidden, which is our array of cards. Okay, let's now the next thing to do is to test and compile this circuit. Go to compiling a circuit. Now I'm going to write a script just so it's easier. So we want to cd into the directory, make a directory, and then we need to download one of these. When you compile your proof, you're going to have a certain number of constraints. So if you choose the wrong file, your compiler will not be able to compile it. Next compiles cards.circum. Okay, so that will compile it. Switch over to snark.js. Now we compute the witness. As we're using one of the powers of tau files, we don't have to do the phase 1. We're going to start here and do some debugging. So next we need to make a Solidity contract which wraps this zero knowledge proof contract and includes the logic for the card game. Okay, so I've filled out the smart contract. I'm just going to go through this function start game, which has most of the functionality. So I'm sending to this function the game ID, the bet, and the arguments, which will then get passed to the verify proof contract. I've got a bunch of requirements which are related to the gameplay, and then I reconstruct the R, S, and V values from the input argument so that I can validate the signature, build up the hash as per the Ethereum signing standard, where you have this prefix followed by the length of the message, 32 bytes. Once that hash has been created, pass that to the EC recover function along with the VRS values to get the signer, and then we check that the signer equals a dealer address. Then we move on to the zero knowledge proof, which is calling this function, which was generated by snark.js, and then we go on to a bunch of gameplay logic. So next I wrote some test scripts. So I've got 2 tests in here so far. I've got the first test simply verifies the zero knowledge proof. So I deploy the contract cards verifier, which was created by snark.js. Then I create a random game ID. I sign it. Then I play about with the R, S, and V values so that none of the values are greater than this number. Then I build up the inputs, and we use the snark.js library to generate the proof and the public signals, and then we call this function export solidity call data to generate the call data, and then we pass that to the contract. And then the second test does the same thing, but instead of calling verify proof, I'm calling this start game function. So let me run this test. Okay, so it's passed both tests. Looking at the public signals, this here is the hash of the hand of cards, which I store in the smart contract. The second public signal is the card that I'm revealing. In the start game, I'm not revealing a card, so that's a 0. And then the last 3 public signals are the R, S, and V values. So when the player starts playing the game, the contract now knows that he is honestly revealing a card from his original dealt hand of cards, because each time he verifies a proof, the contract will see the hash, and the contract will be able to verify that hash matches that player's hand. So the next thing to do is write more test units and make a user interface so that the game is playable.